Welcome to the second part of routing on water resource. I've already uploaded the first part of routing in water resources, and if you want to have a look on it, you can see the description of this video, and you'll get an idea about routing. So flood routing, as I have discussed in the previous lecture, flood routing can be defined as a technique to determine the flood hydrograph at a section of river by utilizing the data of flood flow at one or more upstream section. So, to be more precise, when I predict the downstream hydrograph with the help of the upstream hydrograph, I am using a technique known as flood routing, or routing rather. The routing can be broadly divided into hydrologic routing and hydraulic routing. That means routing based on the methods, it can be divided into hydrologic routing and hydraulic routing. So in case of hydrologic routing, we try to solve or we try to derive the output hydrograph by algebraically solving the equation of continuity. So this is what the hydrologic routing is, and hydraulic routing is of course lumped routing. It is not as accurate as hydraulic routing, where we try to numerically solve the continuity equation along with the equation of motion of fluid under unsteady conditions. So what happens is so as a whole I can say that routing is a technique by which we determine the downstream hydrograph with the help of upstream hydrograph. And as you know, due to the channel section characteristics, roughness coefficients, shape and size of the channel, etc., different factors, the upstream hydrograph will change at any point downstream. And it takes some time to change, of course, because the flood water flows from the upstream points towards the downstream point. And of course there are unsteady flow because there are multiple directional flow can be there in case of water flowing through a channel or water flowing through a reservoir. And there can be lateral flows, there can be longitudinal flows, there can be vertical flows. So this flow is an unsteady flow, not a steady flow. So what happens is, so that is the routing, and routing has two different techniques you can use. Either you can use hydrologic or you can use hydraulic. And in case of hydrologic, you have algebraically solve equation of continuity. And in hydraulic type of routing, you solve the equation of continuity as well as equation of motion for unsteady flow. But in this case, in hydraulic case, you solve it numerically through some programming or some iterative algorithms. But here in this case, you solve the equation of continuity with the help of algebraic equation. There is no need of numerical iterations and all this. So as a result, what happens? Hydrologic routing is lumped. It is not as accurate as hydraulic routing. And however, in case of hydrologic routing also, we have some other method which is semi-distributed, not totally distributed, as hydraulic routing is totally distributed. It is not lumped. But hydrologic routing was further developed to a semi-distributed equation, which is better, which is by result, which is better than the earlier one, the lumped versions, but not as accurate as hydraulic routing. So in this lecture, we will actually discuss about those basic equations: equation of continuity, equation of motion, and how they are used to predict the downstream hydrograph from the upstream hydrograph. So that is our goal of this lecture. So let us begin. Go to the next slide. Oh, before going to the next slide, I want to add some information. You see, routing can be different, can be classified into hydrologic and hydraulic based on the variety of routing methods. But based on the type of water bodies it is applied, you can classify the routing into reservoir routing and channel routing. The name itself suggests that when you are routing in reservoir, it is reservoir routing. When you are routing in a channel, it is channel routing. Reservoir routing means in case of inflow, you have the hydrograph. Now you have to predict the outflow hydrograph. That is the reservoir routing. And in case of channel routing, this is like this, where upstream point you have the hydrograph, you want to determine the downstream hydrograph. And if the difference between this upstream and downstream is crossed by the river at a rapid flow, or to be more precise, rapidly varied flow, where delta is very, very less. Delta means difference of what I can say. If here there is a Q1 and if this is the Q2, so after how much time Q1 has come to Q2? This flow of water has come to this point. After how much time? That is represented by delta. That is, if Q amount of water is here at point 1, after how much time the same amount of water has reached this point 2. So that time is known as delta. So when this delta is very, very small, we say it as, or we refer it as flood routing. So flood routing is actually the same as channel routing or reservoir routing. But if the time taken to reach point 2, this one, from point 1 is very, very less, then that type of routing becomes the flood routing, because that type of flow generally causes flood. Okay, let us go to the next slide, which is our main goal. So basic equations of hydrologic routing. Here I am not considering this hydraulic routing, although in the last step I have discussed a little bit of that. So the basic equation of hydrologic routing is, as I already said, the flood, how the passes of flood, this is the channel, and yes, point 1 I know what is the flow. I want to know the flow here in this second point. So this passage of flood. So here one thing you remember or note that whenever I am discussing about hydrologic, I am discussing about flood routing. Although this flood routing is also known as channel routing, or if it is in reservoir, then it is reservoir routing, that I have already discussed in the previous slide. So what happens is that this is one point, this is the second point. So if I want to determine the hydrograph of this point from the hydrograph of this point, I want to do a routing. Now in case of hydrologic routing, I will use this equation. This is the famous continuity equation, equation of continuity. So it states that at any section of a channel or a reservoir rather, if you deduct the average inflow from the average outflow, if you deduct the average inflow from the average outflow, then you will get the storage, or rather change of storage. As you know, mass cannot be created nor destroyed. It can of course take other forms, but the mass cannot change. And following that equation of continuity, I can write that if you deduct average inflow from average outflow, you are getting the change of storage. Correct? Now for this to be valid, we have two assumptions. Del T, this one del T. Change of storage always have a del T there because it is a time. So if S1 is the storage at T1 after the flood occurs or after the flow occurs, S2 is the storage at T2, time T2. So basically what happens is S2 minus S1 by T2 minus T1 is the change in storage, which is represented by this differential form ds dt. And now what is I? What I have said, I means, suppose this is the point. Now through this point lots of different types of flow is passing. So I means the average of all these inflows. And then what is happening? Average of you can say this is inflow. Let us first say it. Average of the amount of water flowing through point 1, let it be I. And same water will flow through this point 2, E. So let it be described as Q. Okay. So remember, suppose there is the amount of water is Q1. Okay, suppose the discharge is like 10 cubic here at point 1. It flows through the passage of the channel, and when it is reaching here, it is 8 cubic. Suppose for evaporation and infiltration, some amount of flow will get lost. And then suddenly the next time duration we have another flow which is of 12 cubic meter. When it reaches point 2, it is of 10 cubic meter. So basically what happens is lots of different flow can come. Different flow means flow of different magnitude will pass through the point 1. And that same flow somehow reduced, or it maybe somehow it increased also if some rainfall occurs. That amount of flow will cross this point. So the continuity equation say I minus Q is equal to ds dt. Average of inflow minus average of outflow is equal to ds dt. Now this average of inflow means time average, right? You see. Okay. So if I deduct, here you can say this is not, this is Q actually. So actually what happens is if you deduct this the flows passing through that point 2 from the flows passing through the point 1, you get the del S. It is sure. So this equation can also be written as I1 plus I2 divided by 2 multiplied by del T, correct? Minus Q1 plus Q2 divided by 2 multiplied by del T. So I1 is the minimum inflow coming into that section. I2 is the maximum inflow coming into that section. Now you are averaging it. And in case of Q1 and Q2, Q1 is the maximum minimum outflow going out of it, out of the section, and Q2 is the minimum outflow going out of the section. So Q1 plus Q2 is divided by 2. Multiplied by del T. So actually this is your I average, this is your Q average. So you multiply the del T and you get S2 minus S1, this is storage at time 2 minus storage at time 1. This is not point. In this case, this is not point. For S2 is storage of water at time T2. And S1 is storage of water at time T1. But in this case, 1 and 2 is actually indicating, note these differences. I1 is your average, not average, minimum inflow to the section. I2 is your maximum inflow to the section within a time duration del T. And similarly, this Q1 is minimum outflow, right? Minimum outflow from the section, and Q2 is the maximum outflow from the section, and within the duration, same duration del T. So this is actually this one. So this one is I average, and this one is Q average, and you deduct Q average from I average, you get S2 minus S1. And remember, I average is multiplied with the duration del T, and Q average is multiplied with the duration del T. Then only if you multiply this del T and del T, then only you can understand how much amount of water is coming in, comes in, comes out during that del T. So due to this difference, as following the equation of continuity, this S2 minus S1 takes place. S2 is the storage at time T2 and S1 is the storage at time T1. So this one can also be written as del S. Now what happens is, this is the algebraic form. If you want to represent the equation of continuity for this routing, hydrologic routing, with the help of differential equations, then you see this is the del Q by del X. Now X is actually, you see, X indicates the direction. So if this equation is valid, that means there is no lateral flow, correct? Del T is very, very short, such that both inflow and outflow hydrograph can be assumed to be a straight line. And del T must be lesser compared to the time taken by the flood to cross the reach. That means if the time taken for the flood, this flood water, to cross the reach, this is your reach, and say it takes time T, then then del T will be much lesser than this T. So if this is del Q, Q is this water flow or discharge, whatever may be you may say, this is the change in discharge, and divided by change into that X direction, because we are ignoring lateral flow. So if this is the channel, so the flow is always going through x direction, not to y, not to z. And then you add it with the t multiplied del y del t, where t is the t is the top width of the section, channel section, and del y is the depth of the flow, not the channel, not that. Del y is the change in the depth of the flow. Y indicates here depth of the flow, not the channel depth, not that. So what it said? It said that the summation of change in discharge at x direction, del q del x, and this top width multiplied by change in depth with time is 0. So this is the continuity equation. So when we convert this continuity equation to equation of motion, what we do? Del y del x, change in depth, water depth, with respect to that direction x. There is no lateral direction, so only x is here, plus v by g. V is the velocity. Velocity of the flow. G is the acceleration due to gravity, certainly. Del v del x means change of velocity towards that same x direction. Plus 1 by g del v del t, that means change in velocity with respect to time. So there is two components of v, velocity v. One is with respect to x, the direction of flow. Another one is time duration of the flow. So here velocity is considered with respect to the direction as well as the time, and it is multiplied with the v by g. G is the acceleration due to gravity, and also 1 by g, and it was added with the change in depth in the direction of flow, that is x. So if that is the case, then this S0, what is S0? That is a very natural question. S0 is the channel plate slope. Here H2 is the storage at time t2, here in this equation, algebraic form of continuity equation. But when I am talking about equation of motion, this slope becomes the slope of the channel bed slope. Slope of the channel bed slope. And Sm is the slope of the energy line. Slope of the energy line. Okay, so S0 is the slope of the base slope actually. Correct. And whereas S or S final is the slope of the energy line. And V is, as I have said, V is the velocity of flow at any section. When it is divided by del x, it means the change in velocity towards x direction. When it is saying del t, that means change in velocity with time. And for the first one, we have multiplied it with v by g. G is the acceleration due to gravity. And for the second time, we have multiplied with 1 by g. Okay. So that is what it. And here, you know, this is your equation of continuity, and this is your equation of motion. So when you solve this equation of continuity equation with the help of this formula, you are using hydrologic routing, which is lumped. Okay. And of course, this is not accurate compared to the hydraulic routing. In case of hydrologic routing, just you put the values of I1, I2, Q1, Q2. Del T can be noted, both the del T, and put it into the place, put it into the equation, and you will get the change in storage. Okay, so this is the algebraic form, and whenever you convert it into a differential form, it becomes hydraulic routing. which you solve with the help of different numerical methods. It is the iterations method is there, algorithmic methods is there, but numerically you have to solve it. So for numerically solving, these two equations is valid, and for non-numerically solving, that is algebraic solving, this equation is the equation. So this one is actually the equation of hydrologic routing, and whereas this next two equation is the equations for hydraulic routing. Okay, so these are the basic equation of hydrologic routing. I will not say it as hydrologic routing, I will say it as routing, because here I have discussed both hydrologic and hydraulic routing. For hydrologic you use this one, for hydraulic you use this one. So this is as simple as that. But in case of hydraulic routing, you have to numerically solve. This one to be numerically solved, and for this one, this algebraic form, need to be solved algebraically. So this is in a gist is what the basic equations of routing are. So in the next part, I will go deep into hydrologic routing, where different methods of hydrologic routing will be demonstrated, and it is one of them is level pool routing. So I will discuss also the other method, but first I will begin with level pool routing, and I will also try to discuss some numerical examples if possible. So in a summary, what I can say is that flood routing or channel routing or reservoir routing can be done with the help of hydrologic routing and as well as hydraulic routing. In case of hydrologic routing, we are solving the algebraically the continuity equation, correct? And in case of hydraulic routing, we are solving numerically both continuity equation and equation of motion. So that much is what the basic equations of routing. These are the basic equations of. Okay, so thanks for your patience hearing. For the complete tutorial, which is still being updated, along with the numerical examples and project ideas. So I will request you to visit this site and select course number 7. This is the routing course actually. And there are many such courses in that site, Vaipatra, this one. And yes, if you want to do some internship opportunities or looking for some internship opportunities on this topic and relevant topics, certainly go to energyandstyle.org. Okay, so this is what I am to say, and with this I will stop my lecture.